Hello class, this is Mrs. Ayodeji with today's video on 11.3 Euler's method. As you're watching the video, please write down important information in your notes, including formulas, equations, graphs, or statements and examples. Feel free to pause or rewind and replay the video as often as you need so you can get a clear understanding of what is occurring in the video. At the conclusion of watching the video, submit the video as well as a top question via the online list form the day before class. All right, let's begin. Today we're going to be talking about Euler's method, and it is another method for solving a differential equation. If you recall, last video we worked with slope fields as a method to find a solution curve of a differential equation, and that is more of a graphical method. And then today we're going to work with Euler's method, which helps us to numerically find a solution, which basically means numerically is talking about data points or x and y values. And we usually link numerical with a table of values. Okay. Now, Euler was a very famous Swiss mathematician whose work is shown in all throughout math, and you'll see different theorems and different equations attributed to Euler. But this, I think, is one of his best works because it's so simple, but yet it's used to solve differential equations. But the method is involving basic calculus / algebra. So in a nutshell, what does this method do? Well, given a differential equation, you are going to use Euler's method, you need a starting point. And we're going to use, again, the differential equation we're dealing with are first order differential equations. So we're going to use the starting point, x and y values, as well as a differential equation to determine the slope of the tangent line at that point, which is really what the derivative of a function at a point value is. It's the slope of the tangent line at that point. And then we're going to use the slope of the tangent line to determine another point that's on a solution or on the solution. And how do you do that? Well, remember, slope of a tangent line is equal to the change in y over change in x. And if I know what the slope is and I know what the change in x is, I can determine what the change of y is. So oftentimes you're going to have to either pick a change in x that's constant, or you can be given a change of x that's constant. And once we have since we're going to have our change of x, we're also going to be able to use that to determine our change of y, and we're going to be able to determine what the next point using Euler's method is. And you keep repeating steps 2 and 3 until you have enough points to get an idea of what the shape of the curve is going to look like. And you can graph those points, or tabularly you can determine what the shape is going to look like. So before you push pause and rewind to go over what I said, let's look at an example. So in example 1 in the book says, let's use Euler's method for the differential equation dy dx is equal to y. And let's pick the starting point to be 0, 1, and the delta x to be 0.1. Okay? And so make a table, because remember we talked about this being a numerical method. So we're going to use table of values. And our first point, of course, is the starting point with the x value of 0. But because our delta x is 0.1, the future points are going to be 0.1 away from the previous points as far as x coordinates. So now all we need in order to figure out the other solution points is to be able to figure out what the new y value is going to be. In order to figure out what the new y value is, we're going to need to know the slope and multiply that times the delta x at that point. So in this case, since our starting value is 0, 1, then that means that our slope can be calculated simply by taking the y value and multiplying it times our delta x. And then we're going to get our resulting answer, which ends up being 0.1 as well. Lucky that. And we add that to our previous y value to get our new y value for our point. And when we do that, we'll end up with 1.1. and we go through the same process to get to the next point. Since 1.1 is our new y value, we multiply that times our delta x, and we get a new delta y, which is going to be 0.11, and we add that to the previous y value, 1.1, and we end up with 1.21. And so we go through this process over and over and over again to get new y values using the slope of the tangent line and the delta x. And then if you want to get an idea of what that will look like, then we can graph that, plot the points, and we'll get an idea. And as you can see here, it looks like the solution curve is an exponential function, or it could be quadratic, but we know it's exponential because the dy dx is equal to y, and the only function whose is the same derivative is an exponential function. So this supports the idea of our solution. And right off the bat, we have a reason why the Euler's method is not as perfect as we would like. It's because it doesn't give us an equation. It just gives us points that satisfy the solution equation. And we have to use our additional math to figure out what formula or what equation that is. Okay. All right. So let's take a look at example 2. And example 2 asks you to use the same formula, differential equation, and the same starting point. But this time they say they want 2 steps, and they want delta x to be 0.05. But then they want us to determine, will our Euler's method give us a solution coordinate point for, and when x is 0.1, will it give us a y value close to 1.1025? So all we got to do is just try it. So again, we start off with our table, since this is a numerical method, and our first point is 0, 1, and we use this with a change in x to determine our new y value. So as we can see here, this is our change in x. Our slope of the tangent line is the same as our y value, and we get 0.05. Now, because our delta x is 0.05 and we wanted to use 2 steps, then our x values for our points 1 and 2 are going to be x equals 0.05 and x equals 0.1. And so we go through this same process of using the delta y, the slope and the delta x to determine our delta y. And so we end up with a lovely delta y of 0.0525, and we add that. I'm sorry, the first one of 0.05, and we add that to get 1.05, and then we repeat the process to figure out the new delta y, and the new delta y is 0.0525, and we end up adding that, and we get 1.125, which is our Euler method solution, when the actual y value should be 1.1025. So Euler's method, again, will give us a close enough value, but it doesn't necessarily give us an exact value, which reaches the second issue of Euler's method. It won't give us exact values, they just give us approximations. All right, let's take a look at another example. And I like this example because it uses something that in this case, it uses a different differential equation. If you recall, this particular differential equation, the solution is something we've seen before, and the solution is a circle, x squared plus y squared is equal to 1. So we're going to use this Euler's method to determine how well of a solution or how good of a solution we get compared to the actual value. And so here we start off with a starting value of 0.1, and our delta x is being, our starting value is 0.1 and our delta x being 0.1. And so as a result, since they want 4 solutions, we have 4 points. When the x values differ by 0.1, the starting point is 1. We use change in y is equal to slope times delta x. In this case, the slope formula is a little bit different. The slope formula involves negative x over y, so we get initially 0. I draw a circle for some reason. Add that. So that means for the first point, the y coordinate is 1. But then when we use, when we continue using Euler's method, we get different y values, different change in x values. And we end up with something like this. So now we have 4 points. And these 4 points are our estimates using Euler's method. And the true value, since of course we're talking about the solution curve is actually x squared plus y squared is equal to 1. That's how we're able to determine the true value. We compare, and as you can see, the actual true value is about 0.1 off, 0.1 off, 0.2 off. And so the Euler's method solutions are actually overestimates instead of underestimates, and they're not exact values. Okay? And if we were to take a look at the graph, we can see here's our solution curve and here's our slope field. All right. For the last 20 seconds, I'll talk about the accuracy of Euler's method that we talked about. One of the big challenges of Euler's method is that it's an approximation. But the good thing about Euler's method, and we saw with examples 1 and 2, is that when you can improve the accuracy by changing your delta x. So in example 1, we had a delta x of 0.1, and our approximate y value was around 1.1. And our error, so that means our error was 0.05, because this is actually our true value. But in example 2, we used a smaller delta x. We used it as 0.05. And after 2 steps, we had x equals 0.1. And therefore, our y value ended up being 1.1025 when the actual answer was 1.105. So we now have a smaller error when we use a smaller x, delta x. And it seemed like it basically halved the error, which lets us know that the error in using Euler's method over fixed interval is an exact value minus approximate value, and the number of steps we use can be approximately determined that the error is proportional to 1 over n, since we use 2 steps to get to an error of 0.002. And in 1 step, we had an error of 0.05, so it seems like the proportion was 1 over n. Of 1 over n was our solution. All right, that's it. Thanks.